standard second order system closed loop transfer. Okay. So next we have obtained, this is the form we have to remember. C of S by R of S is equal to omega n square by S square plus 2 zeta omega n S plus omega n square. So where omega n is undamped, omega n is natural frequency, undamped natural frequency, units radians per second, where zeta is damping ratio. So this and all we have already discussed in the previous class. Just so damping ratio, it is given by the ratio of actual damping to critical damping. You will get the damping ratio value. So depends upon the zeta value, the response. Okay, so we have to get the response. Response is mainly depends upon two parameters. One is the transfer function parameters and the other one is input. So we have already discussed about the inputs and first order system, different types of inputs applied for the first order system, and we have also obtained the responses. The procedure is same either for first order system or a second order system, but in second order system, so some more parameters we have to observe. In second order system, the denominator consists of zeta and omega n. There are two variables. So depends upon these two parameters. Okay. So the response mainly depends upon, if we assume omega n is some constant value, okay, so the response mainly depends upon this zeta value. So when zeta is equal to 0, undamped response. When zeta is lies between 0 to 1, so underdamped response. Most of these systems come under this case. That's why this is very important case. So third case is critically damped case where zeta is equal to 1. This is an ideal case, almost ideal case. Without any damping, it reaches to the final value. So over damping case. Okay. So mainly there are four cases. So if we apply a unit step function to the second order system, we have to find out response in all these four cases. So the denominator polynomial of a closed loop transfer function is called as a characteristic equation. Depends upon the location of poles, that means the roots of this characteristic equation. The response mainly depends. Okay, the response mainly depends upon this roots of the characteristic equation. That's why the characteristic equation is very important. It plays an important role in control systems. Okay, so the roots of the characteristic equation means these are the two roots we can express in using this equation or this equation. Simply omega d. This can be replaced by damped natural frequency, that is omega d, which is equal to omega n under square root of 1 minus zeta square. Okay. So these are the two. The roots are purely imaginary roots. When zeta is equal to 0, when zeta is equal to 1, the roots are real and equal values. So here, sorry, when zeta is equal to 0, the roots are imaginary. When zeta is equal to 1, the roots are real and equal values. When zeta greater than 1, the roots are real and unequal values. When zeta lies in between 0 to 1, the roots are complex conjugate. Okay, this case is very important case. Okay, now the response we have already seen in the last session. Again, I'm repeating the same. So response of unit step response. This is unit step input. Consider as unit step input whose transfer function is R of S is equal to 1 by S. So second order system, standard second order system transfer function is this one. So standard second order system transfer function, input is same thing. So to get the output, C of S is equal to R of S multiplied with transfer function, T of S, or transfer function. Sometimes it is called as M of S in some textbooks. Okay, so just multiply with this and using partial fractions, so we can get the response C of S. After getting the C of S value, applying inverse Laplace, you will get time domain response of unit step second order system response. Okay, this is the case. We have already calculated A, B, C values using partial fractions. So A, which is equal to 1, B it is -1, C is equal to minus 2 zeta omega n. So simply substitute and we can express the same in this fashion. Okay, so now actual response, just forget about this this part. Now C of s is equal to omega n square. This is input. So where this part is input part, input 1 by s. So this is our transfer function, system transfer function, second order system transfer function. So now using partial fractions, we have already just now we have done that partial fractions for this portion. So you will get 1 by s minus s plus 2 zeta omega n s by s square plus 2 zeta omega n s plus omega n square. This is our equation. Now, so just manipulating this part, that is expressed, the denominator of this function is expressed like this. So s square plus zeta omega n square. If we expand this one, s square plus zeta square omega n square plus 2 zeta omega n s. So this is expansion plus omega n square minus 2 zeta. So minus zeta square omega n square. Minus zeta square m square plus zeta square m square gets cancelled. Finally, you will get the same value. That's why I have expressed the same thing in this fashion. And this part I have replaced with omega d. So we have that equation omega d is equal to omega n under square root of 1 minus zeta square. That's why I have substituted instead of this term simply. So we can substitute omega d. Okay. So now the numerator can also be expressed in the same fashion because we have inverse Laplace of s plus a by s plus a whole square plus omega n square is e to the power of minus at into cos theta. Similarly, omega by s plus a whole square plus omega square, inverse Laplace for that is e to the power of minus at into sine omega. So that's why I have expressed the same thing. Okay, just like zeta omega n term and one more zeta omega n term. Okay, second term again zeta omega n term is multiplied and divided with omega t so that you will get in this fashion. Okay, just manipulating. Okay, so next. So now taking inverse Laplace. So in the last class we have done up to that part. Okay, I think. So now let us continue the same derivation. Taking the inverse Laplace, we will get 1 minus e to the power of minus zeta omega n t into cos omega dt. Now I have replaced with just applying inverse Laplace. The term can be replaced with in terms of time domain, that is cos omega dt minus zeta omega n square by sine omega dt. Okay, is it clear? $278. If you have any doubts, you can raise. Okay. Number 278, 19B8 1A0 278. If you have any doubts, you can raise your doubts. So this is very important derivation and answer final response. We have to remember this answer. Okay. Now C of s is equal to this same thing. Now what I'm doing here is simply omega dt, 1 minus e to the power of minus zeta omega nt into cos omega dt. Now cos omega dt, if we multiply, if we take multiply with under square root of 1 minus zeta square, so if we multiply the entire term with, multiply and divide with the same term, otherwise we can take the denominator term as common. So you will get 1 minus e to the power of minus zeta omega nt under square root of 1 minus zeta square. If we take this term as common, so you will get under square root of 1 minus zeta square into cos omega dt plus, so here the only the numerator term zeta sin omega dt. Okay, so this term is common, so that's why I have taken this term as common, and the denominator in the denominator, so if we take this term as common, you will get the same in the numerator. Okay, final expression is this one. Next, and using this triangle, so right angle triangle, so if we assume theta is angle, opposite side by adjacent side, that becomes sin theta, and that is, which is nothing but simply zeta this term can be replaced with sin theta so construct a right angle triangle so that you will get theta here square root of 1 minus zeta square zeta and 1. So if we multiply squares of these two sides, you will get unit value. So from this triangle, we can express sin theta is equal to under square root of 1 minus zeta square, cos theta is equal to zeta. And we can also write tan theta is equal to under square root of 1 minus zeta square by zeta. Simply using this right angle triangle, so we can replace this term. Okay, so this is sufficient, but for the sake of simplicity, we can easily remember this answer. So to get this answer, so simply replace this under square root of 1 minus zeta square with sin theta and zeta with cos theta. So if we observe this equation sin theta, sin A cos B plus cos A sin B, we can write it as sin A plus B. Okay. Sin A cos B plus cos A sin B, we can simply replace with sin A plus B. So finally, now the response of a second order system, with unit step input is 1 minus e to the power of minus zeta omega nt under square root of 1 minus zeta square sin omega dt plus theta. So this is very important. Okay, so we have to remember this answer, where theta is equal to tan inverse of under square root of 1 minus zeta square by zeta. Okay, now we have obtained the response of second order system when that is nothing but the closed loop response. So simply for unit step input, the same answer you will get. For a step input with a different magnitude, just simply multiply with that particular magnitude value. Okay, now this is the response. If we plot, if we substitute values, okay, for different values of time, if we substitute the values, you will get a response something like this. This is a second order system response when the input is unit step. Unit step means when the input is given like this, so it reaches to final value, the system reaches to final value. So after a certain time, it consists of both transient as well as steady state periods. Okay, so in transient period, if we observe, it reaches to a maximum value. Okay, and again it is an oscillatory response, and finally it reaches to the final value. Okay, unit. Okay, so because of this sinusoidal term sine omega t plus theta, if we observe, the response is an oscillatory response. So e to the power of minus at, it is exponentially decaying function. So combination of these two, so automatically the response is a damped oscillatory response. It reaches to the steady state value after a certain time. Because of this exponentially decaying function, the oscillations decreases. Okay, the oscillations are due to this sinusoidal function. Okay, simply if we substitute the values, you will get the response something like this. Okay, next, coming to the next case. This is the case where the zeta value lies in between 0 to 1, in between 0 to 1. Simply if we want to, if we substitute zeta is equal to 0, you will get this response for undamped case. So otherwise, so we can solve the same. Again, using partial fractions, you will get the same response. Try to do on your own. Okay, just I'll go a little bit faster. In this case, simply substitute zeta is equal to 0 in the closed loop standard transfer function, and we know that r of s is equal to 1 by s. Simply 1 by s multiplied with the transfer function, you will get c of s in frequency domain, in s domain. Now to get the response in frequency domain, to get the response in time domain, simply use partial fractions. Okay, a by s plus b by s square plus omega square. So here the response is the same second order system, but in case of undamped case, zeta equal to 0. So find out a and b values. You will get 1 by s minus s by s square plus omega n square. Simply note down this part. Okay, simply note down this part and try to do the partial fractions on your own. So finally, because inverse lap, we have inverse Laplace of cos omega t is s by s square plus inverse Laplace of s by s square plus omega square is cos omega t. That's why I have written in this fashion. So finally, you will get a response when zeta is equal to 0. So whose response is 1 minus cos omega nt. So previous case, when zeta value is lies between 0 to 1. Here that is when zeta is equal to 0. And we can also solve when zeta is equal to 1. That is critically damped case. So here the response is an oscillatory response. It never becomes 0, even though if we substitute the values, set cos theta is equal to 0, it starts with 0. At cos 90, you will get uh, cos 0 is 1, you will get 0. Cos 90 is 0, you will get unit value. At cos 180, you will get minus 1. So it becomes twice the value. So it is something like this. The response, if we substitute the time values, omega t values, so for the same unit step input, the system never reaches to 0. It is an oscillatory system. Okay, there is no damping. So without any damping, so it never comes to 0. It is an oscillatory system. So it is lies in between. The response always lies in between 0 to 2. Okay. So in the previous case, because of that exponential term, exponentially decaying term, e to the power of minus t, these oscillations reduce it to 0 or steady state value. Here the state, there is no question of steady state. It is okay. Steady state means the value which is obtained, that itself is, this is a stable system, but it is an oscillatory. It never becomes, it never reaches the input. Okay, it never reaches the input. So next case, critically damped case, when zeta is equal to unit. So when zeta is equal to unit, simply same thing, same procedure we have to follow. R of s is equal to 1 by s, multiply with this, and using partial fractions, in this case, a by s plus b by s plus omega n whole square plus c by s plus omega n. So this is the function we have to find out, partial fractions. So in this case, we have to find out a, b, c values. Okay. This is critically damped case when zeta is equal to 1. The response, if we calculate the response, it is something in this function. The first one, 1 by s. So 1 by s means its Laplace transform is, inverse Laplace transform for 1 by s is unit value. So 1 by s square, that is t into e to the power of minus at, 1 plus s, whose inverse Laplace for this is e to the power of minus at. When 1 by s into, 1 by s plus a whole square, whose transfer function, whose inverse Laplace is t into e to the power of minus 80. Same thing what I have substituted here. Here t into, so e to the power of minus 80. Inverse Laplace of this function. So this is 1 by, again the Laplace e to the power of minus 80. This is inverse Laplace for that. So the response in this case, critically damped case, there is no oscillatory part, critically damped system. So there is no sinusoidal function, there is no oscillations, only the when the term sine or cosine term are present in this equation, so then only you will get that oscillations. Otherwise, there is no question of oscillations. It is an exponentially decaying function. So it is decays with respect to time. Okay, note down this. Only just note down this part, that itself is sufficient. Do the partial fractions on your own. So try to do or practice these derivations so that you will get confidence. Okay, so you can solve examples based on the same partial fractions. Okay, the response for the system, if I observe, it is in critically damped case, without any oscillations, it reaches to the final value. Okay, so starting from 0, if it is exponentially, it is a rising function, so it reaches to unit value. So up to this part. Okay, without any oscillations, it reaches to unit. So now, so if we observe all the combination of for different values of zeta, if we observe the response. So for first case, when zeta is equal to 0, when zeta is equal to 0 case, it is an oscillatory response. It never becomes to the unit value, or it never reaches to this. Okay, only except at an intermediate points. So it is an oscillatory response. As we increase zeta value, so if we increase the zeta value, the oscillations gets reduced. Okay, so when it comes to these two are underdamped case. So when zeta is equal to 0.2, when zeta is equal to 0.4, or when zeta is equal to 0.8. Okay, so the oscillations will get reduced as zeta value increases. So when it reaches to unit value, critically damped case, directly it reaches to, without any oscillations, it reaches to final value. Final value is this, our C of t final, not C of t, this is R of t. Input is unit step function. So R of t unit value. Okay. So as we increase, that is overdamped case, theta greater than 1. Overdamped case, the system becomes very slow. That means to reach the final value takes more time. So more time to reach its final value. It is a very slow system or sluggish system. It is also called as sluggish system. It reaches the final value without any oscillations, but the time taken to reach the final value is very high when zeta value is more than unity. Okay. So these are the curves different for unit step response curves for a second order system. Okay. Now, if we observe the locations of poles and zeros, so this is pole location for second order system. So as the zeta value is when zeta value is equal to 0, when zeta is equal to 0, the poles, that means the roots of the, so in the beginning itself I have told that zeta value, that means S1 and S2 roots. Okay, initially when zeta is equal to this, I have told here at the beginning, when zeta is equal to 0, S1 plus S2 is equal to, there is no real part, only purely imaginary roots. Okay, the characteristic equation, the roots of the characteristic equation, that means this one characteristic equation means the denominator polynomial of a closed loop transfer function is called as characteristic equation. Very, very, very important equation this is. The response mainly depends upon the roots of this characteristic equation. So when the roots of the characteristic equation, they are purely imaginary. Okay. Now they lie on the, so here they are purely imaginary when zeta is equal to 0. Next, if we increase zeta value, so oscillatory system response this is. Okay. So when the roots zeta value increases, it is a damped response, gradually becomes 0. Okay, unit value, sorry, not 0. So it reaches to steady state value. So when zeta lies in between 0 to 1, here the roots are complex conjugate roots. So that's why as they move in this direction, so this root moves in this direction. So as zeta value reaches to unit value, again the roots become purely real and equal roots. So at intersection point, that is then at zeta is equal to unit value, so that is an ideal case. So where the response without any oscillations within shorter time, it reaches to the final value. Okay, when zeta is equal to unit, critically damped case, so the response is without any oscillations, it reaches to unit value. So even after that, if we further increased, one root moves towards 0 and other root moves towards infinity when zeta is equal to greater than 1. Here the roots are again purely real but unequal values. One root is moves towards this origin, the other roots reaches to infinity. So this is a pole zero diagram. So based upon the location of roots, we can guess the response. First, we have to remember that. So based on the roots of the characteristic equation, we can guess the response, whether it is critically damped case, over damped case, under damped case, or undamped case. Okay. Otherwise, if we know zeta value, we can guess the response. maybe an underdamped response or oscillatory response or critically damped response. So if we know any of these values, we can guess the response, we can guess the output, whether it is a stable one or not. For example, if we observe the roots are low are on right side of the right half of this S-plane, this is called S-plane, real one, real axis, imaginary axis. If the roots are lying on right half of the S-plane, the response is something like this. As t tends to infinity or t goes on increasing, the system becomes uncontrolled. So it is not a stable system. So for a stable system, the roots must lie on this side of this S-plane or this um, graph. Okay, the roots must lie on the left half of the S-plane. If the root, any of the root present on the right half of the S-plane, the system is said to be an uncontrolled system or unstable system. Simply our entire meaning control systems is mainly depends upon the location of the roots. How you will get that roots? Just roots of the characteristic equation. Characteristic equation means what? It is the denominator of a closed loop transfer function. Okay. So the closed loop transfer function denominator is called characteristic equation. The look, if we just find out the roots, the location of the roots directly gives whether the system is stable system or unstable system. Next, based upon the location of roots, we can guess the response, whether it is overdamped, underdamped, undamped, or critically damped case. And we can also guess the response. So in which fashion, whether it is reaching or it never reaches to steady state value or it is a sluggish system. So everything, the entire thing can be obtained by simply the location of the roots. So that's why this plot is very important. Just try to understand this one. Okay, if you have any doubts, you can raise it afterwards. Okay. Next. Coming to time domain specifications. Now we have to, so there are two responses. One response, there are two responses, okay, whose zeta value is, whose zeta values are 0.5 and 0.6. Both are underdamped responses. Okay, but which one is more stable? How to find out that? Okay, so for that, the time response, okay, is the time domain specifications are an indicative for the quality of the response. Which one is more stable? How to find out that? So using some indices, we can find out, we can tell this response is good response when compared to other one. So one is getting 90%, the other one is getting 92%. Which one is better means 92. How you will get that 92%? Based on some mathematics marks, based on some physics marks, based on some chemistry marks, based on some other subject marks. Okay, so like that, the same thing here. The response, the entire response is specified, or quantitatively we can say using some indices. They are called time domain specifications. Okay, time response specifications or time domain specifications, and also so transient response specifications. Everything will come in transient period only. Okay, so when it reaches to steady state value, only you will get one indices, that is steady state error, whether it is reaching to steady state value or not. So if it reaches to steady state value, no problem. Okay, so after it reaches to steady state steady state value, whether it reaches the reference input or not. So our aim is unit value, but it reaches 99.99. So that means 0.001 is an error. With 0.001 error, it reaches the steady state value. 0.1 error, it reaches the steady state value, or otherwise 1% error, it reaches the steady state value. Like that, we have to calculate the error. In steady state period, the specification is only error value. But in transient period, there are so many indices. This is nothing but these are the specifications. One is delay time. The first specification, it is time taken to reach 50% of its final value is called as delay time. That is first specification. The second specification is called as rise time. How much fast it rises to its final value. Rise time, time taken to reach its 100% of its final value. That is called rise time. And one more time, that is peak time, time taken to maximum value. Okay, so that is called peak time. And settling time, time taken to reach its steady state value, final value, that is called as steady state. So these are the specifications to represent any time response. This becomes the specifications. Just a minute. Note down this response. ఓకే, నోట్ చేసుకున్నారమ్మా? Just I'll read this one. Control systems are generally designed for with damping less than 1. Generally, most of the cases, most of the practical systems are having zeta value which is less than, always it is less than unit value. Even though higher order systems having a pair of complex conjugate poles with damping less than 1, which dominates the over the other poles. So generally this complex conjugate poles response is dominates the other poles response. So because of this, the final resultant response is damped oscillatory response. So always once we observe, or generally the time response is specified in terms of this these specifications, or so generally any response, any for any system, so we can consider the response as an oscillatory response. So once the oscillatory response, that can be, the response can be specified using the following specifications. Okay, so step response has number of overshoots and undershoots with respect to final value. Before reaching this final value, so before reaching the final value, it is having some overshoots and also the undershoots. Okay, This type of response is characterized by following performance indices. These indices are quantitatively related to how fast the system moves to follow the input. So whenever some input is given, some signal is given, the system has to respond. Immediately the system has to respond, or it follows the input, respond to the input. Okay. So how fast the system moves to follow the input. Second one, how oscillatory it indicates it is, or indicative of damping. How does, how long does it take to practically reach the final value? So these are the questions. Okay. So how fast it reaches the, it follows the input. A smart system, smart boy means immediately whenever if a question is asked, so immediately if anybody is responded, that is how fast he is responding, that becomes a smarter one. Okay. And how oscillatory it indicate it is. How oscillatory means depends upon the zeta value, whether it is without any oscillations it reaches to final value. So that means a critically damped case. So but when zeta value is 0.8, it is having less oscillations. When it reaches to near to 0, that means 0.1, so it has more oscillators, no more oscillations. So it is, even though it is stable, but it is an oscillatory, more oscillations it is having, so it is not, it is less stable when compared to the system having zeta value 0.8. So if we compare two systems whose zeta value is 0.8, whose zeta value is 0.1, so zeta is equal to 0.8 is more stable when compared to zeta is equal to 0.1. How oscillatory it is. Okay. How long does it take to practically reach the final value? How long it takes to reach its final value? So these are the questions. Okay. Related, quantitative related to indices. Okay. Transient indices. Okay. So this is the response, oscillatory response. Just now I have told these are the time domain specifications or also transient specifications. One more specification just now I have just forgot to told, this is peak overshoot. Peak overshoot means it is above the final value. So it is time taken, or it is, okay, not the time taken. So how much it is more than the final value. So that is called as peak overshoot. Mathematically, you can show that one later. Okay. Now, the time response of unit step function depends upon the initial conditions. Okay. Here, initial conditions are very important. The transient response, that means this response previous just now, this part is transient part. Up to this, it is transient part. Before that, it is transient part. After this, it is a steady state value. So this is a tolerance period. We can eliminate this one. That means, so at this time it reaches the final value. Okay, 2 to 5% tolerance is allowable in control systems in most of the practical cases. So 2 to 5% is allowed. Okay. So now here the initial conditions are very important, but while doing the derivations we assume that initial conditions are equal to 0. Okay. And all its time derivatives, the first derivative and second derivative thing is assumed to be 0. Now the specifications can be defined like this. The delay time, transient response specifications, or time domain specifications, both are same. Transient period means up to settling time. Time domain means including this steady state error. Okay. So now the delay time means it is time taken to reach the response to reach half of its final value from the initial instant, 0 instant. So time taken to reach 50% of its final value is called as delay time. So rise time means the time taken to reach 0 to 100% of its final value in case of underdamped system. In case of overdamped system, because it is a sluggish system, slowly it increases. So time taken to reach is 10 to 100% of its final value is called as rise time for an overdamped system. Okay. So coming to the next specification, peak time. So peak time means it is the time required for the response to reach the peak value of it for the first time. So time taken to reach its peak value, first peak that we have to consider. Okay. So that is called as peak time. Peak overshoot. Peak overshoot means just now I have told it is represented with MP. The peak overshoot is defined as the deviation of the response at peak time from the final value of the response. Okay, so this is just now I have shown in this figure. So this is called peak overshoot. So this is final value, but this one is peak value. So this is called as peak overshoot, very important one. So this is called peak overshoot. So it is final value. Okay. Final response C of T at TP at peak time minus the final value. C of T. So the difference between these values, this is C is equal to C at TP and this is at infinity. So that means response after settling when t is equal to infinity time means it reaches to steady state value. The difference between the C of TP and C of infinity is termed as peak overshoot. Is it clear? This is the peak overshoot is defined as the deviation of the response at peak time from the initial value of the response, from the final value of the response. It is called maximum overshoot or peak overshoot, that is called. Now coming to settling time, it is time required for the response to reach the steady state and stay within the specified tolerance band around the final value. It is called settling time. So finally it reaches the final value. The generally 2 to 5% tolerance is allowable in all practical cases. So the settling time, the tolerance band is 2 to 5%. Now coming to the steady state error. So this is an error. The term indicates steady state error. Error means it is if we kept a reference value as 100%, if we reach 99% means 1% error. So it is an indicative of error between the actual output and the desired output. So actual output means whatever be the value of time, that is called actual output. The desired output means our aim. So we expect 100%, but it reaches to 98% means 2% error. Okay, so it is an indicates the error between the actual output and the desired output as time tends to, this is not tends, it is time tends to infinity. As t tends to infinity, so whatever be the value remains, that is called steady state error. Okay, these are time domain specifications. This is time steady state specification. Total these time specifications are called time response specifications. Okay, I think so. Have you noted down? Have you noted this? Okay, now we have our aim is to find out this time domain specifications for a second order system. So second order system is very important. Second order system and underdamped case when zeta is equal to lies in between 0 to 1. Zeta may be any value. Okay, so find out time domain response, because whatever be, even the higher order system or second order system, everything is a damped oscillatory system. The damped oscillatory system, we have to specify the response using these specifications. Okay. So peak time means time taken to reach its peak value simply. So here, if we the time from 0 to TP, so time taken to reach the maximum peak value, okay, in the first time. So even though it is also a peak, this is also a peak, but we have to calculate only first peak. Okay, is it clear? So time taken to reach 50% of it is called as delay time. Time taken to reach 100% in the first time is called rise time. Time taken to reach its maximum value in the first time is called peak time. Time taken to reach final value, okay, that is steady state value, is called settling time. This is called settling time. Okay, is it clear? So peak overshoot. So again, okay. So peak overshoot, or it is called maximum overshoot. Maximum overshoot means this is called as maximum overshoot. So here, this is final value. This is the maximum value, the response at this point, that is C of TP at maximum value. Okay. So here the response is having more than this final value. This is nothing but the deviation. Okay. So that is called a peak overshoot or maximum overshoot. Here the response value is something more than the final value. The final value is this one, that is C at T settling time. Okay, that is its final value. T at settling time or T at infinity value, everything is same. So at settling time, so it is having whatever be the value at settling time, the same thing remains at T is equal to infinity. So that is the value. The difference between these two is called as peak overshoot. Is it clear? Peak overshoot means it is the deviation. So here, that is the peak overshoot is defined as the deviation of the response at peak from the final value of the response. This is called as peak overshoot. Is it clear? If anybody is having doubts, you can raise. Okay. Now, our aim is to find out the expressions. Now, the expressions for time domain specifications. Mathematically, we have to express. So we have already represented, we have obtained the response, mathematical equation for the response. That is C of t is equal to 1 minus e to the power of minus zeta omega n t by under square root of 1 minus zeta square sine omega dt plus theta. That is the response of a second order system, what we have done earlier. Now, I want to express, I want to get formulas. Simply, I want to get formulas for peak overshoot, for rise time, peak overshoot, and settling time, everything. So for time domain specifications, that is how to get this means just to by solving and by using the definitions, we can find out the mathematical form of rise time and mathematical form of settling time, everything. So note down these equations. I will come back just within a minute. So note down this. So how to get expressions for time domain specifications? So first one, so we know that the response of a second order system is this one. Now based on the definition, rise time means that it is the time required to reach 0 to 100% of its final value. So our final value means it is unit value. Okay, so finally it has to reach unit value. So that's why C of that is represented, rise time is represented with T suffix R. So TR is equal to 1. So equate this response. When T is equal to TR, okay, if we substitute T is equal to TR, this entire term becomes unit value. Okay, from the definition, rise time is time required to reach 100% of its final value. Final value is unit value because it is a unit step response. TR value is unity. Okay, the final value is unit value. So at T is equal to T rise time, it is unit value. So if we observe the graph, this is the graph. So at T is equal to TR, at T is equal to TR. Okay, so it reaches to its final value, that is unit value. C of TR is unity. When T is equal to TR, its value is unity. Okay, so then therefore simply calculate TR value using this term. So this is unit value. Now simplify that one. So when if we take this 1 and -1 gets cancelled, 1 and 1 gets cancelled, finally that term is 0. So this term cannot be 0. So e to the power of minus zeta omega n TR. This is rise time. Undamped natural frequency omega n, damping factor 0 zeta. These terms cannot be 0. Only the term that can be 0, which is only sine omega dt r plus theta is equal to 0. So this term can be 0. Whereas for an underdamped system, zeta cannot be 0. So because this is an underdamped system, okay, zeta lies in between 0 to 1. Okay, so zeta cannot be 0, TR cannot be 0. Okay, if it is TR rise time is equal to 0 means it never becomes to there is no, within no time it is reached to final value. So that cannot be possible. So this entire term cannot be equal to 0. Only the term that can be equal to 0, that is sine omega dt plus theta. So equate it to 0. So we can get the rise time, that is pi minus theta by omega t. So 2 pi 0 2 pi pi 2 pi everything. So for a first time, what we are calculating is only first time. That's why we have considered it as pi. Omega dt r plus theta is equal to pi. From the TR is equal to rise time is equal to mathematically pi minus theta by omega d. Where omega d means omega d is equal to under square root of omega n into under square root of 1 minus zeta square. So we have to replace theta is equal to minus not tan inverse of under square root of 1 minus zeta square by zeta. Okay, so simply substitute that one, we will get the complete formula for rise time. So these formulas are very important. TR is equal to pi minus theta by omega t. So if we substitute omega d and theta, so finally the rise time can be expressed in terms of seconds. TR. Theta or tan inverse of that value should be measured in radius. While calculating problems, we have to express in radians. Note down this. If you have any doubts, you can raise. Okay. So next, coming to second specification, that is peak time. So everything is same. మనకి కొంచెం మ్యాథమెటిక్స్ మీద గ్రిప్ ఉంటే అసలు మనం ఏమీ చదవక్కర్లే. సింపుల్ లాప్లాస్ ట్రాన్స్ఫార్మ్స్, simple differentiations, integrations and differentiations. Okay, peak time means it is the time required to reach its peak value for the first time is called as peak time. So peak time means the response if we observe at the peak. So this is the response. Input is unit value. So the response starts from 0 and it reaches something like this, and again it comes back. So at t is equal to 0, this is called as peak time. Okay. At this time, the slope of the curve is 0. So that's why to find out the maximum value, okay, t by dt of c of t at t is equal to tp equal to 0. That is the mathematical point we have to, using this, we can find out the peak time. Okay, at d by dt, c of t at t is equal to tp is equal to 0. That's why we know the response c of t for a standard second order system, the formula that is c of t is equal to the given formula. Okay, this is the standard second order system response. At t is equal to tp time, if we substitute t is equal to tp, so at this tp time, c d by dt of c of tp is equal to 0. Okay, so at t is equal to tp time, at this point, its derivative, first derivative is 0. Okay, same thing I have substituted and solved for this to find out tp. Differentiating c of t with respect to time. So again, we have to use some uv formula. So uv dash minus vu dash. Okay, by v square. So note down this simply. So this was the simplified equation. So d by dt of c of t. So you will get something like this. Now again, substituting back, this zeta can be substituted with cos theta. Cos theta is equal to zeta. Sin theta is equal to 1 square root of 1 minus zeta square. Substituting using this right angle triangle. So we can further simplify it as sin a cos b minus cos a sin b, cos a sin a minus b formula. Sin a cos b minus cos a sin. Okay, sin a minus b formula. So after simplification, finally you will get omega n by under square root of 1 minus zeta square is equal to e to the power of minus zeta omega n t sin omega dt. Okay, if you have any doubts, you can ask in this part. Okay, next, at t is equal to tp time, at t is equal to tp time, so c of t is equal to the first derivative, which is equal to 0. Okay, so 233. switch off your mic. 20B8 5A0 233. If you have any doubts, you can ask. Otherwise, please switch off your mic. So T is equal to TP time. So if we equate it to 0, so substitute and equate it to 0. So again, this part cannot be equals to 0. Only that can be possible. Only TP is equal to sine omega dt, omega d, TP equal to 0. So this term can be 0 because for an under-damping system, zeta cannot be 0, the frequency cannot be 0, peak time cannot be equals to 0. So that's why this term never equals to 0. Only the term which can be equals to 0, which is sine function. So equate that one to 0. So you will get a peak time. TP is equal to pi by omega t. So the second peak occurs at this point. Okay, 2 pi by omega t. For third peak can be obtained after the time 3 pi by omega t. So therefore, mathematically the peak time can be expressed using this formula pi by omega d. We have to remember this one. Now 233, please switch off your mic. Otherwise, if you have any doubts, you can ask. 20B8 5A0 233. Okay, so please note down this. That is peak time. Next, coming to peak overshoot. So peak overshoot, MP, it is defined as the deviation of the response at peak time. So deviation of the response at peak time from the final value of the response. So mathematically, the percentage, that is percentage peak overshoot is defined as percentage MP, which in terms of final value. So this is peak value minus final value by final value into 100. That is called peak overshoot. Peak response at t is equal to TP. Final steady state value is t at infinity. At a t is equal to settling time or t at final value. T infinity means. So t at infinity is unit value. So that we know. Okay. C of t is equal to C of infinity is equal to unit value. It reaches to steady state value after infinity time. So t at infinity is 0. Now t at peak time. So peak time just now we have calculated, that is pi by omega d. So at a t at a TP, so TP means substitute TP instead of TP, pi by omega d. This is the formula we have to substitute and simplify this equation. Finally, you will get something like this: 1 plus e to the power of minus zeta pi by 100 square root of 1 minus zeta square whole divided by 1 minus zeta square into sine theta. Please note down this. In between, if you have any, so this is for d equal to TP. Now, again, the same after simplification, you will get the responses something like this at its C at a TP. Now substitute back in the formula. Percentage overshoot is equal to CTP minus C at infinity by C at infinity. Same C at infinite value is unit value. So this value is 1 plus e to the power of minus zeta pi by and square root of 1 minus zeta square. Simply, after simplification, we have to remember this formula. Percentage overshoot, very important formula. This is percentage overshoot. So if it is more than very high, so that generally in case of motors, in case of generators, or case of wires, the insulation level mainly depends upon this peak overshoot values. Okay, whether it is twice or thrice more than the final value. So the insulation way thing, everything is mainly depends upon this peak overshoot. That's why it is very important. Peak overshoot is equal to e to the power of minus zeta pi 100 by 1 minus zeta square into 100. Okay. So that is about peak overshoot. Any doubts regarding the rise time, peak time, peak overshoot? If you have any doubts, you can raise. Otherwise, you will stop here and we'll continue in the next session. So try to remember, try to practice these derivations and try to remember these formulas also.
Pedro?
Okay. Any doubts? Otherwise, we'll end this session for today. Only 66 means attendance is very, very, very poor.